Hello and welcome. This is your host, the Electric Starman. Tonight, we turn our gaze toward the most patient, unforgiving architecture in the known universe, the black hole. For decades, these entities existed purely as mathematical anomalies, ghosts hidden inside Albert Einstein's field equations of general relativity. In late 1915, Karl Schwarzschild sat near the Eastern Front during World War I, battling severe illness while calculating the precise geometry of space around a single, dense point of mass. He found a boundary, a point of no return where the escape velocity strictly equals the speed of light. Einstein himself was skeptical, suspecting that nature would never allow such extreme singularities to actually collapse into real physical existence. Yet, as our instruments grew sharper, the universe proved far stranger than our early theories dared to predict. From the discovery of Cygnus X-1 in the 1970s, through its energetic X-ray emissions, to tracking the hypervelocity orbits of stars circling the invisible mass at our galaxy's center, and finally to the historic Event Horizon Telescope images capturing the direct shadows of supermassive giants, black holes shifted from theoretical ink on paper to tangible cosmic anchors. Tonight, we explore both the physics and the human story of these silent abyss makers. We'll examine the accretion disks of supermassive giants, the strange dilation of time near the event horizon, and the brilliant minds who slowly peeled back the dark. As always, all music you hear tonight is composed specifically for this journey. Now adjust your listening level, let your mind rest, and let us drift into the silent geometry of deep space. Consider the winter of 1915. The world outside is cold, fractured, and loud. Yet inside a quiet mind, on a frozen front line, a German astronomer named Karl Schwarzschild sits with paper, ink, and Albert Einstein's newly published equations of general relativity. General relativity describes gravity not as a pulling force, but as the bending of space and time by mass. Einstein had provided the broad framework, the 10 complex field equations that tie space, time, matter, and energy into a single continuous fabric. But Einstein believed exact solutions to these equations were impossible to find for real physical systems. The mathematics were simply too dense, too tangled in nonlinear differential geometry. Schwarzschild, despite battling a severe autoimmune disease called pemphigus, set to work calculating what space would look like around a single, perfectly spherical, non-rotating mass. He worked slowly, line by line, setting the electric charge to zero, setting the angular momentum to zero, and reducing the infinite complexity of space-time down to a pristine, elegant metric. When he finished the calculation, he had produced the very first exact solution to Einstein's equations. It is known today as the Schwarzschild metric. Embedded within Schwarzschild's metric was a strange mathematical feature, a threshold located at a specific radius from the center of the mass. This critical radius, r sub s, depends entirely on the total mass of the object. If a mass can be compressed down smaller than its critical radius, the curvature of space becomes so steep, so absolute, that the escape velocity exceeds the speed of light. For our sun, this critical radius is roughly 3 kilometers. For the Earth, it is less than 1 centimeter. At the time, physicists viewed this radius as a mere mathematical artifact, a coordinate singularity born from idealizing a mass into an infinitely small point. It seemed physically impossible for a star to collapse that far. The pressure of atomic matter, the repelling forces between electrons and nuclei, would surely stop the collapse long before such a boundary could form. Einstein himself read Schwarzschild's paper with admiration, but remained convinced that nature possessed built-in protections against such ultimate collapse. Yet the equations did not lie. The metric revealed that at this boundary, the role of space and time reverses. Outside the radius, a starfarer can move forward or backward in space, but is relentlessly swept forward in time. Inside the boundary, time becomes the spatial coordinate, pointing inexorably inward toward the center. To avoid the central singularity inside this horizon is as impossible as avoiding tomorrow. The Schwarzschild solution showed that as light climbs out of a heavy gravitational field, it loses energy. Its waves are stretched, shifted toward longer, cooler, redder wavelengths. This is gravitational redshift. Near the critical boundary, this redshift becomes infinite. A photon emitted right at the threshold loses all its energy attempting to climb the potential well, dimming down to absolute silence. Schwarzschild sent his paper to Einstein from the front lines in December 1915. 5 months later, Schwarzschild passed away from his illness, leaving behind a silent, mathematical seed. For decades, it remained dormant, a curious theoretical boundary buried deep within theoretical physics. A door without a key, a shadow waiting for the sky to catch up to the math. For half a century, the dark boundaries predicted by Schwarzschild remained purely theoretical. Ground-based optical telescopes looked out at stars and gas through a thin blanket of atmosphere, blinded to the violent, energetic phenomena of the cosmos. Visible light shows us warm stars and glowing gas clouds, but the processes surrounding compressed mass emit energy far beyond the visible spectrum. To find a black hole, humanity had to learn to look at the sky in X-rays. Earth's atmosphere absorbs incoming X-rays, protecting life below. To see the high-energy universe, scientists had to push instruments above the air. In 1964, small sounding rockets carrying simple Geiger counters were launched into the upper atmosphere for brief, precious minutes of observation. When the detectors scanned across the constellation Cygnus, they picked up a bright, fluttering pulse of hard X-ray radiation. It was designated Cygnus X-1, the first X-ray source identified in the Swan constellation. In 1970, NASA launched Uhuru, the first dedicated X-ray astronomy satellite. Uhuru orbited above the atmosphere, systematically scanning the sky and mapping Cygnus X-1 with unprecedented precision. The X-ray emission was not steady. It flickered rapidly, changing brightness on timescales of milliseconds. This rapid flickering was a crucial clue. A physical object cannot change its overall brightness faster than the time it takes for light to travel across its width. If Cygnus X-1 changed its intensity in a few thousandths of a second, the region producing those X-rays had to be tiny, no larger than a few hundred kilometers across. Yet, when astronomers aimed optical telescopes at the precise coordinates of the X-ray source, they found a massive, glowing blue supergiant star known as HDE 226868. How could a massive, bright blue star produce high-energy X-rays while flickering on millisecond timescales? The answer lay in binary orbital dynamics. HDE 226868 was not alone. It was orbiting an unseen dark companion. By measuring the Doppler shifts in the blue supergiant's spectral lines, astronomers calculated the orbital period and determined the mass of the invisible partner. The dark companion had to be at least 14 times the mass of our Sun. No normal star, neutron star, or white dwarf could remain stable at 14 solar masses without collapsing under its own gravity. The maximum mass limit for a stable neutron star, the Tolman-Oppenheimer-Volkoff limit, is roughly 2 to 3 solar masses. Anything heavier must succumb to total gravitational collapse. The process of X-ray generation in Cygnus X-1 is a study in friction and gravity. The massive blue companion star expands, spilling its outer hydrogen gas across the Roche lobe, the gravitational boundary between the two objects. This gas is captured by the dark companion's gravitational field. Because the captured gas possesses angular momentum, it cannot fall straight down. Instead, it swirls into a flat, rotating structure, an accretion disk. As gas orbits closer to the center, inner rings move much faster than outer rings. Viscous shear stress, friction within the magnetized plasma, slows the gas down, causing it to spiral inward. This friction converts gravitational potential energy into heat. In the innermost regions of the accretion disk, temperatures climb to millions of degrees Kelvin. At these thermal energies, the plasma glows brightly in the X-ray spectrum. Cygnus X-1 was not emitting X-rays from the dark object itself, but from the superheated accretion disk swirling around its horizon. The theoretical horizon had finally left a physical signature on the cosmos. While stellar mass black holes like Cygnus X-1 formed from the deaths of individual massive stars, a vastly larger mystery lay buried at the center of galaxies. For decades, astronomers wondered what engine could power the intense, compact radio source designated Sagittarius A star, located 26,000 light-years away at the exact rotational center of the Milky Way. Dense dust clouds along the galactic plane block all visible light from this region. To peer into the core, astronomers had to wait for infrared technology to mature. Beginning in the 1990s, two independent teams, one led by Reinhard Genzel at the Max Planck Institute, and the other by Andrea Ghez at UCLA, began decades-long monitoring campaigns using near-infrared detectors mounted on world-class telescopes. They used advanced techniques, including adaptive optics, to correct for the blurring distortions caused by Earth's atmosphere. Instead of seeing a blurry, smeared smudge, adaptive optics sharpened the view, revealing a dense cluster of individual stars orbiting in the deep gravitational well of the galactic core. These fast-moving stars became known as the S-stars. Year after year, decade after decade, Genzel and Ghez tracked the precise positions of these stars. One star in particular, designated S2, provided the definitive key. S2 moves along a highly eccentric, elliptical orbit around the dark position of Sagittarius A star. In May 2018, S2 made its closest approach, sweeping past the central object at a distance of less than 20 billion kilometers, roughly 3 times the distance from the Sun to Pluto. At its closest approach, S2 accelerated to an astounding velocity of nearly 3% of the speed of light, roughly 7,600 kilometers per second. By applying Kepler's third law and the equations of general relativity to S2's complete 16-year orbit, Astronomers calculated the mass of Sagittarius A star with extraordinary precision. It contained 4 million times the mass of our Sun, packed tightly into a space smaller than the orbit of Mercury. No star cluster, no dense cloud of subatomic particles, no hypothetical collection of dark matter could remain stable within such a small volume at that mass. It would inevitably collapse into itself. Sagittarius A star was conclusively proven to be a supermassive black hole. Furthermore, as S2 rounded pericenter, its light exhibited the exact gravitational redshift predicted by Einstein, alongside the relativistic precession of its orbit, tracing out a delicate rosette shape over time rather than a stationary ellipse. The heart of our galaxy was not a chaotic vacuum, but a clean, silent gravitational anchor around which billions of stars, gas clouds, and solar systems serenely perform their multi-million-year dance. In 1963, nearly half a century after Schwarzschild derived his spherical metric on the Eastern Front, a New Zealand mathematician named Roy Kerr discovered the exact solution to Einstein's field equations for a rotating mass. Until Kerr's breakthrough, astrophysicists operated under the idealization of stationary black holes. But stars in our universe rotate. When a massive star collapses, its conservation of angular momentum demands that its spin rate accelerate dramatically, much like an ice skater pulling in their arms. The Kerr metric describes the true dynamic geometry of real astrophysical black holes. A spinning black hole possesses two critical boundaries rather than one. The inner boundary remains the event horizon, a spherical or oblate surface of absolute causal isolation. But surrounding the event horizon is an outer, ellipsoidal boundary known as the static limit. The spatial region sandwiched between the static limit and the event horizon is called the ergosphere. The word ergosphere derives from the Greek word ergon, meaning work. It is a region where the fabric of space-time itself is not merely warped, but dragged along in the direction of the black hole's rotation. This phenomenon, known mathematically as frame dragging, or the lens-thirring effect, means the space itself rotates around the central mass. Within the ergosphere, no physical object can remain stationary relative to a distant observer, no matter how powerful its propulsion system. To remain static would require moving faster than the speed of light against the rotational current of space-time itself. Because space-time inside the ergosphere rotates so violently, energy can theoretically be extracted from the black hole's spin. In 1969, British physicist Roger Penrose calculated that a particle entering the ergosphere could split into two fragments. If one fragment falls inward past the event horizon, along a trajectory of negative energy relative to an observer at infinity, the remaining fragment can escape into deep space with more kinetic energy than the original parent particle possessed. The extra energy is drawn directly from the rotational kinetic energy of the black hole, slightly slowing its spin. At the absolute center of a Kerr black hole lies not a zero-dimensional point, but a ring-shaped singularity of zero thickness and non-zero radius. This ring singularity sits within the equatorial plane, spinning infinitely fast in coordinate time. Surrounding the ring singularity, gravity exerts extreme differential tidal forces on any infalling matter. As an object approaches the horizon, the gravitational gradient, the difference in gravitational acceleration between the near edge and the far edge of the object, grows exponentially. For a stellar mass black hole, this tidal gradient becomes so fierce that it stretches matter vertically along the line of fall while compressing it horizontally, a process known as spaghettification. The molecular bonds of matter are overcome, stripping atoms down into individual subatomic particle streams long before they reach the central ring. When interstellar gas, or a companion star's outer atmosphere, approaches a black hole, it rarely falls directly inward. Because the infalling plasma carries angular momentum, it settles into an orbit within the equatorial plane, creating a high-density, swirling structure known as an accretion disk. The physics governing these disks combine general relativity, fluid dynamics, thermodynamics, and electromagnetism into a field known as magnetohydrodynamics. In a thin Keplerian accretion disk, first modeled comprehensively by Rashid Sunyaev and Nikolai Shakura in 1973, the orbital speed of the plasma increases closer to the center. Adjacent, concentric rings of plasma slide past one another at different velocities, generating powerful, viscous shear stress. This shear stress converts orbital energy into intense thermal heat, causing the disk to glow brightly across the electromagnetic spectrum, from optical wavelengths at the cool outer edges to hard X-rays in the turbulent inner region. As the plasma spirals closer to the event horizon, it reaches a point of no return for circular orbits. The innermost stable circular orbit, or ISCO. Outside the ISCO, plasma can orbit indefinitely in stable concentric rings. Inside the ISCO, stable, circular orbits become physically impossible under general relativity. The gas can no longer maintain an orbital equilibrium and plunges dynamically inward toward the horizon in a steep, rapid trajectory. Because the plasma in the innermost disk orbits at a substantial fraction of the speed of light, relativistic beaming, also called Doppler boosting, transforms our view of the system. Light emitted by plasma moving toward an observer is compressed in wavelength and focused into a tight forward cone, appearing significantly brighter and bluer. Conversely, light emitted by plasma moving away from the observer is stretched and dimmed, appearing redder and fainter. This creates an asymmetric visual appearance where one side of the accretion disk appears dramatically brighter than the other, regardless of intrinsic disk symmetry. Threaded throughout the ionizing plasma are powerful, tangled magnetic fields. As differential rotation twists these magnetic flux tubes into tight, spring-like coils along the rotational axis of the black hole, magnetic reconnection events release tremendous quantities of stored energy. In 1977, Roger Blanford and Roman Zanagic demonstrated how these twisted magnetic fields, anchored in the ergosphere of a rotating Kerr black hole, can electromagnetically extract spin energy directly from space-time. This process accelerates electrons and positrons to extreme relativistic velocities, launching collimated, ultra-dense plasma jets perpendicular to the accretion disk. These relativistic jets shoot outward across thousands of light years, carving gigantic lobes of radio emission into the surrounding intergalactic medium. one of the most striking predictions of general relativity is that mass bends the trajectory of light. Photons carry energy and momentum, traveling along paths called null geodesics through curved spacetime. When light from distant background stars or an encircling accretion disk passes near a black hole, the severe spatial curvature acts as an extreme gravitational lens, bending light rays along sweeping curves. Outside the event horizon of a non-rotating Schwarzschild black hole, at a distance of exactly 1.5 times the Schwarzschild radius, sits the photon sphere. At this precise radial threshold, gravity is strong enough to force photons into unstable circular orbits. A hypothetical observer standing in the photon sphere and pointing a beam of light sideways would watch the photons circle the black hole and strike the back of their own head. Because these orbits are inherently unstable, any minuscule perturbation will cause a photon to either plunge inward across the event horizon or escape outward to infinity. Because the photon sphere captures and redirects light from all surrounding angles, it acts as a critical boundary for distant observers. Photons that pass slightly outside the photon sphere are deflected around the central mass, creating warped, double, or circular images of background objects known as Einstein rings. Photons that cross inside the photon sphere are inexorably drawn down into the horizon, leaving behind an apparent void of light. To a distant observer, this dark region appears significantly larger than the physical event horizon itself. This optical effect is known as the black hole shadow, due to the intense gravitational lensing of photons escaping from near the photon sphere. The apparent diameter of the shadow for a non-spinning black hole is roughly 5.2 times its Schwarzschild radius, a specific mathematical ratio derived from the impact parameter of light rays. When supercomputer simulations trace millions of individual photon paths through the curved spacetime around a black hole, the resulting imagery reveals a bright, narrow ring of light surrounding the central shadow. This photon ring is composed of subrings, formed by photons that have completed half orbits, full orbits, or multiple complete revolutions around the central mass before escaping toward our instruments. The inner edge of the bright accretion disk appears bent over the top and bottom of the black hole, creating an optical illusion where the rear of the disk is magnified and elevated into a halo above the shadow. over half a century, classical general relativity held that black holes were absolute sinks of matter and energy, objects from which nothing could ever escape. But in 1974, theoretical physicist Stephen Hawking applied quantum field theory to the curved spacetime surrounding an event horizon, revealing a profound paradox that united quantum mechanics, thermodynamics, and gravity. According to quantum field theory, the vacuum of space is not an empty void, but a dynamic sea of virtual particle-antiparticle pairs constantly popping into existence, interacting, and annihilating back into pure vacuum energy within time limits dictated by Heisenberg's uncertainty principle. Normally, these virtual pairs annihilate almost instantaneously, leaving no net energy behind. Hawking calculated that near the event horizon of a black hole, the extreme gravitational gradient can separate a virtual particle pair before they can annihilate. One particle of the pair falls inward across the event horizon into a region where its energy relative to a distant observer is negative. The other particle escapes outward into space as real, observable radiation carrying positive energy. Because the infalling particle contributes negative energy to the central mass, the net result is that the black hole loses mass, while an external observer detects a steady stream of thermal radiation escaping from the horizon. This quantum emission is known as Hawking radiation. Hawking radiation possesses a pristine, black-body thermal spectrum. Its exact temperature, known as the Hawking temperature, is inversely proportional to the mass of the black hole. A supermassive black hole containing millions of solar masses has a Hawking temperature measured in fractions of a nanokelvin, far colder than the 3-degree Kelvin cosmic microwave background radiation, meaning it currently absorbs more ambient energy from the cosmos than it emits. However, as a stellar mass or mini black hole slowly loses mass via Hawking radiation, its mass decreases, causing its horizon temperature to rise. As it shrinks, its temperature increases exponentially, accelerating the rate of energy radiation. In the final fraction of a second of its existence, a black hole dissipates its remaining mass in a high-energy flash of energetic gamma rays and subatomic particles, leaving behind a pristine, empty vacuum. This thermodynamic dissipation demonstrates that black holes are not truly eternal. They possess a finite entropy, the Bekenstein-Hawking entropy, which is directly proportional to the surface area of their event horizon measured in Planck units. In the deep, cold future of the universe, long after the last stars have burned out, even the vastest supermassive giants will slowly evaporate into thermal photons, returning their mass back to the quiet fabric of expanding space. The established model of stellar evolution dictates that black holes are born from the deaths of massive stars. When a star exceeding roughly 20 solar masses consumes its internal nuclear fuel, its core inevitably collapses, triggering a supernova. The resulting stellar mass black hole begins its long existence at roughly 5 to 15 times the mass of our Sun. Standard physics dictates that this singularity can grow by accreting surrounding gas or merging with another black hole. But there is a limit, the Eddington limit, to how fast a black hole can feed, as the outward radiation pressure from the heated accretion disk eventually overcomes the inward pull of gravity, halting the food supply. This growth rate is slow, requiring immense timescales to build up mass. In the early 2020s, however, the launch of the James Webb Space Telescope, humanity's premier infrared observatory, shattered this sequential understanding of black hole growth. The telescope, JWST, peered back through billions of light years of expanding space-time to look at the universe as it existed less than 500 million years after the Big Bang. Deep field surveys revealed fully formed, actively feeding supermassive black holes containing hundreds of millions, sometimes billions of solar masses, glowing fiercely as quasars in the very infancy of cosmic time. These discoveries created a profound causality crisis in modern astrophysics. Stellar mass seeds simply could not have accreted enough mass, even at the fastest possible theoretical rate, to become supermassive so quickly. The math did not add up. The universe had skipped a billion-year growth phase. This paradox gave rise to a revolutionary hypothesis: direct collapse black holes, or primordial seeds. In the pristine, metal-poor environment of the early universe, vast clouds of neutral hydrogen and helium could grow exceedingly massive and cool without the fragmentation caused by heavier elements or premature star formation. Instead of collapsing into a single, hypermassive star that would immediately supernova and leave a standard stellar remnant, these immense primordial gas clouds, perhaps 100,000 solar masses or more, could have undergone a dynamic, direct, monolithic gravitational collapse. A vast, cohesive sphere of hydrogen, bypassing the star stage entirely, plunging past its own Schwarzschild radius to form an instant, high-mass seed. These 90,000 solar mass direct collapse seeds provided the necessary head start. They did not begin at the mass of a single star. They began at the mass of an entire small star cluster. With such a massive starting point, these seeds could rapidly outgrow the Eddington limit through rapid mergers and efficient hyper-accretion, achieving supermassive status in a few 100 million years. As JWST continues to analyze the infrared spectroscopy of these high redshift quasars, astronomers are searching for the key spectral lines that would indicate a chemical signature born of direct collapse. we are watching the first anchors of the cosmos form, not through a long, quiet evolutionary process, but through a violent, unprecedented, dynamic restructuring of pure primal gas. For over a century, black holes remained theoretical or indirect entities, ghosts detected only by the X-rays generated by their heated food or the erratic orbital dance of neighboring stars. We could map the effects of their immense mass, but we could not resolve the dark, unlit horizon itself. This limitation was not a failing of curiosity, but a fundamental barrier of optical resolution. Sagittarius A star, the 4 million solar mass black hole at the center of our galaxy, is physically massive, but its vast distance, 26,000 light-years, gives it an angular size in our sky roughly equivalent to seeing a single donut placed on the surface of the moon. Resolving that tiny angular diameter requires an observatory with a theoretical mirror thousands of kilometers across. In 2017, humanity overcame this resolution barrier by turning the entire planet Earth into a single, synthetic radio telescope. This extraordinary project, the Event Horizon Telescope, or EHT, utilized a technique known as Very Long Baseline Interferometry. The EHT synchronized a global network of powerful radio observatories spanning from the ALMA array in high-altitude Chile to the South Pole Telescope, the SMA on Mauna Kea, and dishes across Europe and Arizona. Each dish in the array was atomic clock synchronized and tuned to receive millimeter wavelength radio waves. These millimeter photons, emitted by the hot, magnetized plasma surrounding the black hole, can pass completely unimpeded through the thick dust clouds blocking the galactic core from visible light telescopes. For weeks, the global dishes all pointed at the same precise coordinates in the sky, collecting unprecedented petabytes of raw radio wave data. These waves, carrying the slight phase offsets caused by the thousands of miles separating the dishes, had to be physically collected on hard drives and transported to a central supercomputer facility in Massachusetts. This raw data required nearly 2 years of monumental processing to account for atmospheric variations, digital noise, and geographic inconsistencies. It was not a single image, but an intensive data synthesis process, integrating millions of data points from diverse locations into a coherent, radiometric map. In April 2019, the EHT collaboration released the historic first direct image of a black hole, the supermassive giant M87 star at the heart of the Messier 87 galaxy, followed later by Sagittarius A star. The image revealed a bright, slightly asymmetric golden ring of radio emission, just as relativistic Doppler beaming had predicted. Inside this golden ring sat a profound, unambiguous central darkness. The image resolved the black hole shadow, the result of photons bending, looping, and ultimately plunging inward past the photon sphere and event horizon. We were not merely mapping the neighborhood. We were analyzing the exact geometry where light itself fails. The Event Horizon Telescope had finalized the long journey from Karl Schwarzschild's theoretical paper to the tangible architecture of the cosmos. We must conceptualize the black hole not as an unstable vortex or a destructive anomaly, but as the quiet, final state of maximum equilibrium. They are the most stable structures in the known universe, enduring long after stars have fused all their fuel, long after galaxies have exhausted their gas, and long after the universe has expanded into a cold, entropic void. For trillions upon trillions of years, the stellar graveyard will grow. The remnants of countless star systems, now locked into stable, cold orbits around these central anchors, will slowly spiral inward. Mass, momentum, and energy will continue to collect, perfectly preserved within the infinite causal decoupling of the event horizon. In this distant future, the geometry of a black hole dominates all reality. Their presence provides a form of stable galactic metabolism. By pulling in surrounding matter and generating intense radiation in plasma jets, they prevent overdensities and regulate new star formation, sculpting the spiral arms of their parent galaxies with gravitational finesse. A supermassive black hole is not a parasite. It is the silent regulator, the dynamic stabilizer, preventing the chaotic gravitational collapse of 100 billion stars. Without the central stabilizing mass, the orbits of stars would lack a clear anchor, potentially leading to widespread chaotic interactions and stellar ejections that would destabilize the structures necessary for life to form. The most profound quality of the black hole is its final quietude. For the vast majority of its multi-trillion-year existence, a black hole is not an active, feeding quasar, glowing violently across the cosmos. It sits, cold and silent. Once it has consumed the surrounding matter, the accretion disk cools and dissipates. The X-rays cease. The relativistic jets fade into faint radio echoes. The once violent structure settles into a serene, mathematical architecture. An observer sitting in a stable orbit, outside the tidal gradients of the ergosphere, would see nothing but a pristine, circular lens, a distortion of the cosmic microwave background, a mathematical curvature defined purely by mass, charge, and angular momentum. We are drawn to these structures not through fear of their immense gravity, but through a deep, restful respect of their quiet finality. They are the ultimate cosmic memory storage, archiving all matter and information that crosses their threshold within the microscopic surface entropy of their event horizon. As the universe continues its long, dark, accelerated expansion, black holes provide the only places of perfect stability, enduring gravitational anchors that outlast time itself. To rest our minds upon the black hole is to embrace the ultimate equilibrium, a perfect, final silence, born of extreme geometry, waiting patiently in the cold of the endless void.